So why do we expect gravitational waves from these sources in the first place? So if the neutron star is spinning and it's a perfect sphere, basically, then we do not have any emission of gravitational waves. However, if there's some sort of asymmetry or imperfection, or in slang, a mountain in the star, on the star, then we will have emission of gravitational waves. And these waves will be different from the ones that we have observed so far, which have an spiral, emerging phase, and ring down phase. These will actually be, since the source is isolated and it continuously emits gravitational waves, then we would expect continuous waves. And this is basically a quasi-sinusoidal wave, quasi because of the emission of gravitational radiation, electromagnetic radiation. The star loses angular momentum energy, and therefore the frequency decreases with time. And we can describe this continuous waves with two sets of parameters, which are lambda, the phase parameters, and a, which are the amplitude parameters. So lambda has to do with the Doppler modulation due to Earth's motion, the source frequency, and the further spin downs of the source. And the amplitude parameters a have to do with the signal amplitude and the source orientation. So as I said, pulsars lose energy because of this emission of gravitational radiation, electromagnetic radiation. However, some young pulsars undergo glitches, which basically is a spin-up event that is an anomaly in the frequency evolution of the star. So instead of continuously slowly decreasing, the frequency suddenly goes up, as you can see in this plot. And then this sudden event is followed by a relaxation phase with timescales from hours to days, also months. And what does this mean? Because energy cannot be created out of nothing, right? So we have to seek the answer in the interior of the star. However, we don't know anything about that. Well, we do know something, but it's mostly unknown, so we can't test it out with observations. However, there are some models out there that explain these anomalies. For example, the two-fluid model is a very competitive model, which explained the anomaly due to a transfer of angular momentum from the inner superfluid component of the star to the outer crust of the star, the normal fluid. And gravitational waves could be produced from the freed energy in this transfer of angular momentum. So from glitching pulsars, we do not really expect continuous waves because they're sudden events, they're particular events, but they aren't even transients because they have a time scale and they're continuous waves. So they're kind of something in between transients and continuous waves, and that's why we call them transient continuous waves. So we can model these transient continuous waves starting from the continuous wave signal model. So we have our phase and amplitude parameters, lambda and a. But in addition to these parameters, we also can consider a set of transient parameters, namely tau, which is the duration of the signal, and t naught, which is the start time of the signal. So basically, if you see in the sketch on the bottom, the transient continuous wave is basically a continuous wave model modulated by a window function that depends on these transient parameters tau and t naught. So in this example here, we have a rectangular window function that effectively turns on the wave at t naught and turns it off at t naught plus tau. So what's the methodology to detect these signals? We can start from the signal versus noise hypothesis framework. So we have our two hypotheses, the only Gaussian noise in the data hypothesis and the signal hypothesis, which says that we have, in addition to Gaussian noise, we also have a transient continuous wave signal. And for each one of these hypotheses, one can compute the likelihoods and then the ratio. And then the standard procedure consists of maximizing the likelihood ratio over the parameters, the amplitude parameters A. And what you obtain here, I'll spare you the mathematical details, but you obtain this statistic, which is called the F statistic. And here in this plot, you can see for each combination of tau and t naught, the transient parameters, you have a certain value of the F statistic. And if you want to remove completely the dependence on from the transient parameters, then you can either maximize over the transient parameters or also marginalize over the transient parameters. And in the first case, you just obtain very naively the max f. In the second case, you obtain something a little bit different, which is called BTSG. And here we take the logarithm just because it's easier to work with. And these are final detection statistics that we use in transient continuous wave searches. So before going on, I just want to make some remarks on the F statistic and what it represents in our data. So in continuous wave analysis, the building blocks of the data are called short Fourier transforms, or SFTs. And you can see them here in action in this plot, the frequency time map. You can see here that the output is quite digitalized, and that's because each pixel corresponds to a certain time segment, which corresponds to a certain SFT. So that's the data that we have. And these timestamps are usually, these time segments are usually 1800 seconds, but this can vary depending on the analysis. And the F statistic, which comes from the maximization of the likelihood ratio that we talked about, what it does is it coherently sums up the power along the correctly Doppler demodulated track with the antenna pattern weights. So basically, in simple words, it tells us how much power has accumulated in the data. And to compute the F statistic, it's not an easy task. The software that we use uses an implementation that basically combines the F statistic atoms, which are 7 numbers that are associated to these antenna pattern functions and the projection of the data on a complex basis, and then combines these F statistic atoms to finally get the final detection statistic that we want. And all of this is then kind of inserted in the context of match filtering. So we always use match filtering in the traditional methods, which basically consists of choosing a template bank covering a certain parameter space of interest. For example, here's a template bank of a certain range of frequency and spin down of the star, and each dot corresponds to a template. And for each one of these templates, we compute the detection statistic, and for example, the max F or the log V, and then we are interested in the highest statistic over the full template bank, which could be possible candidates of transient continuous waves. And previous searches have covered a parameter space lambda given by electromagnetic ephemeridis, and the transient parameters were chosen in more or less these ranges. So basically, half an hour to 120 days for the duration of the transients. T0, the start time of the signal, is usually it's in an interval centered at the time of the glitch, and with a wiggle room of a day. And then for a rectangular function, previous searches have always used a rectangular function. However, one can ask themselves, well, the rectangular function isn't really very physical because signals don't turn on and turn off in time like that. Maybe something more similar to a exponentially decaying window function would be more physical. Or maybe even transients can be delayed from the time of the glitch, and they can start very, like 2 days later, or 3 days later, or maybe a month later. So what about these parameter space ranges? Unfortunately, these searches were limited in these transient parameters because you have to compute the partial sums of the F statistic atoms corresponding to all the combinations of the transient parameters. And if you have a window function that's different from the rectangular function, then things get even worse. So for this particular problem, we want to use machine learning to kind of explore different parameter ranges and also enable different types of window function as a search. So just to put this in context, these are the results from this traditional method that have been found in the LBK paper that has been published in December or January of this year. And we have searched for transient continuous waves from 9 glitches. So each one of these subplots corresponds to a different glitch. And these are the 95% upper limits on the amplitude of the transient continuous wave as a function of tau, the duration. And the black dots here are the actual upper limits, and the red line corresponds to the energy constraints on that glitch. So basically this formula here, because given a certain glitch, pulsar with a certain distance from Earth, then there's a maximum amplitude gravitational wave that we can get from that glitch. And that's basically the red line. So you can see here in these results that we do not beat the energy constraints for any of these pulsars. So we think that machine learning could help us at least get closer to beating those upper limits, and by using more physical parameter space ranges. So to do this, we use convolutional neural networks that have proved to be really good for gravitational wave data on continuous waves. They are a deep learning algorithm that's really good at picking up patterns, and they are very much used for image recognition. They use filters that convolute with the input and output these convolutional feature maps that then pick up these patterns. And as we've already said before in other talks, you usually have stacks of convolutional and max pooling layers. Then you flatten the output of these convolutional layers, and then you add fully connected layers for the output. So going back to the fstat atoms, if we interpret these 7 numbers, 7 per timestamp fstat atoms as pixels of an image, then we can feed them into a CNN. And that's exactly what's the idea here. So we use this intermediate output of match filtering, which doesn't do the very expensive part of match filtering, to feed it into a CNN. And the outputs could be, for example, the probability of belonging to a signal noise category. So we have basically classification. And the threshold on that output can be set by fixing a false alarm probability, and you get a threshold. So this is our first draft model. So we didn't put much thought into it yet. We just basically use what's the standard procedure. So stacks of convolutional max pooling, flatten the output, add a dense layer, and then the output is a certain it's just you just put it a sigmoid activation function, and then you're good to go. So about the classification, so that's what we initially tried to do. The CNN outputs a ad hoc created detection statistic, which is between 0 and 1. But then we thought maybe there's another way to do this, which could be better and give us more information. So we thought of this different approach that uses regression instead of classification. So instead of getting a detection statistic between 0 and 1, we can get also a continuous target that's between 0 and infinity. And as a target, we thought of using the signal-to-noise ratio, the SNR, which would be interesting because it would label how strong the signal in the input is. And then you can treat this output, this SNR that you get, just as you would treat a classification output. So you set a threshold by fixing the false alarm rate, and then you say noise or signal for that particular input. So this is our first setup that we use, the testing and training set distributions. For the testing set, we use an unbalanced data set, so 100K noise samples and 10K signal samples. And for the training set, we use the balanced data set, so 20K noise samples and 20K signal samples. So before going into the results, I wanted to make some remarks on the performance of the CNN and how we understand it. This is all work in progress and what we've kind of learned along the way. So first of all, we have to define the search setup. So we have to know which parameter space we want to target. We have to know which signal and noise distributions we want to explore. And of course, then we want to compare this CNN output, the performance, to the match filtering performance. So usually you do this with ROC curves, which are probability of detection versus probability of false alarm. And to actually compare apples with apples, you have to choose a testing set for your CNN that is as close as possible to real search outputs. And actually, it's very important, the testing set, when you choose it, because noise samples determines how deep you go with the probability of false alarm, and the signal samples of the testing set determines the resolution of this curve, basically. And finally, the CNN model gets as good as its training set. So, of course, this will be defined based on the data we want to search for, we want to target. So these are some very early results. here you can see the ROC curve for match filtering in red, and for the CNN in dashed blue. And match filtering is still the most sensitive thing to do. Here we're only using Gaussian plus simulated injections, and we tested also on different sky positions and data with realistic gaps in it. And this is all nice, but unfortunately, as you can see in this plot on the right, which is a scatter plot of the duration tau of the injectant signals and the SNR of these signals, you can see that the red crosses are the false dismissal. So what we haven't seen in our CNN, what the CNN hasn't picked up. And you can see that there's a false dismissal rate of 12% at false alarm probability of 1%. So, and you can also see here that they're all the false dismissals are accumulated towards 10, like they're less than 10 SNR. So seeing this plot, we thought of maybe trying a different training strategy. And here comes curriculum learning. So curriculum learning is a training strategy that consists of training on data sets of increasing difficulty. There are previous studies that have used the curriculum learning on gravitational wave data. So here's some references. And for our detection problem, we choose as a difficulty criterion the SNR. So basically, we first train on high SNR data, and then we train on low SNR data. And why we choose the SNR? Well, you can see it here, for example, in this plot. So these are the distributions. The noise and signal distributions of the match filtering detection statistic. And in black is the noise one, and the colored ones are associated to the signal distributions. But the blue is associated to a low SNR range, so from 4 to 10, and the green is associated to a high SNR range, so from 6 to 40. And we had to cut the x-axis here, but you can see that the green actually goes up to about 1,750 of detection statistics. So the overlap with the noise distribution is very, very small. While on the other hand, the blue curve, which is the lowest in our range, its overlap with the noise is quite high, and all of those points that overlap, they confuse the network. They're the ones that are kind of confusing our network. Yes. So we tried curriculum learning with these two ranges from first from 6 to 40 and then from 4 to 10. And you can see the ROC curve. We have, again, in red, the match filtering performance, and then the dashed blue is the CNN standalone, so without curriculum learning, and the solid line is with curriculum learning. And the testing set is the same. So you can see here that curriculum learning actually outperforms the standalone model. So we do have an improvement, and in fact, you can see this also in the false dismissal rate at PFA 1%. So from 12% of false dismissal rate, we go to 7%. So this of course has still room for improvement, but we think that we can push this a little bit more, and maybe, for example, with curriculum learning, adding intermediate data set and push a little bit forwards. And obviously, these are preliminary results. I basically got these plots last week. So we still have lots to do with our CNN network. We have to fine-tune the parameters, which is an important step. And we also, of course, want to use this on real data and make this software available for people to use. So we have a little bit to do on our to-do list, but these are just first results. So conclusions, machine learning represents a complementary tool for traditional match filtering techniques. We do not want to replace the match filtering because sometimes match filtering is still the best thing to do. But this could be very helpful also to improve the data quality, the quality of our upper limits, and to explore new parameter space regions. In fact, we will test this on the exponential window function, which would be very exciting and was prohibitive, unfortunately, in the traditional searches. Our model currently allows for flexible amplitude evolution, but it does not allow for frequency variation beyond the standard spin-down model. So to have this flexibility, we have to actually change the inputs of our CNN model. We would have to use, in this case, directly the SFT data from the detector. So currently we're using these intermediate outputs from match filtering, but in this case we would have to use exactly the frequency time maps, for example, directly from the detector. So this is already a future project that we're planning, and yeah, we'll get to it. But first, we want to kind of explore what we can do with this first model that we have designed and how far we can push it. So I am done. Hope I'm in time, and thank you for listening. And if you have any questions or suggestions, I'm happy to hear them.
Thank you, Oana, for this interesting talk. Do we have any questions?
Hi, thank you so much for the talk. It was very interesting. So I wanted to go back a bit before conclusions. I think there's this plot where you use curriculum learning.
Yes.
So my problem, no, one less. Yeah, this one. So from the back, I don't see the y-axis in the left. Can you tell me what the y-axis was again?
In the left plot, the left plot,
Yes.
it's the probability of detection versus probability of false alarm, the ROC curve.
Okay.
You also see a true positive rate and false positive rate usually.
So one thing that helped me out aside from curriculum learning was also to penalize network, like to lower the false alarm rate. Because I think it's actually quite relevant that you can control how many examples you're going to classify as good or false. So for that you can set a threshold, or you can make the network learn it by itself. So I think maybe that could help aside from using curriculum learning.
Okay, yeah. As I said, we just did a first test to see for a proof of concept, you know. But yeah, I'm like we can talk this over as well during the coffee break, because I'm very interested in your inputs, because I think that you actually use curriculum learning as well.
Yes.
Okay. Yeah. So yeah, I added your reference. So.
Yeah, so far it looks super good.
Okay. Thank you. It's great to have that feedback from you.
Thank you. Yes, Michael.
A small question also about curriculum learning, because there is usually this notion of that if you try too hard and the network starts to forget. Did you observe something like that in this case?
Yeah, actually, to prevent this, I think something you could do would be to, instead of just using two different data sets, easy one and a difficult one, you can use an easy one and then use the easy plus difficult one. So in that case, you train again on the full data set, and you would prevent the model from forgetting. That hasn't been implemented here, but I think there's actually a paper that implements this in order to do exactly what you just said.
So that would be this hyperparameters kind of fine-tuning also.
Yes. So the hyperparameters fine-tuning is also for the, like here I'm referring more to the CNN design. So basically numbers of filters and all the numbers of layers inside the network itself, because we basically just tried something that worked by hand, and then we want to do that like more systematically. But yeah.
Yeah, but the hyperparameters in terms of balancing the training set could also be.
Yeah, exactly. Yeah. That's a work in progress. Obviously, we're kind of exploring and doing tests on these both testing sets and training sets, and yeah, and kind of learning along the way. But yeah, absolutely, we know the importance of tuning the hyperparameters of the training and testing sets, and yeah.
Okay, thanks. I think that Isa first asked me it yet. But it is like first question, second, third. It is difficult.
Thank you very much. So, sorry for being a little late to come back. Anyway, I have two, let's say, general questions, not only for you, but maybe for everyone. And maybe it's two big questions that, you know, anyway. So I have two questions. One is, how easy is to fine-tune the parameters? And the second one related is, are you sure you are not missing a best option?
So
just one comment. I think it is not like for you only, but in general, from let's say not so expert like you, okay? But I always have these two questions: how easy is to tune parameters, and are you sure you don't have a better option you are not aware maybe? So these are the two questions for you and also for the rest of the people.
Okay, so starting from the first question and the fine-tuning of the hyperparameters, what you can do is, so if you use, for example, TensorFlow, there's this function that's grid search CV. So basically, you choose a certain, it's kind of like a template bank. So you choose a certain range of, for example, batch size and number of layers and so on. And that basically just does the grid search. So it runs on each combination of these hyperparameters that you have chosen. So again, it's always kind of, it's discrete. It's not like a continuous thing, but it gives you an idea of how the network would behave going in one direction or the other. As for the second question, I think that's quite a philosophical question. So basically, I don't think you ever know if it's the right one because with machine learning, I think you just have to find the best minimum in the fits that you can find by hand or with fine tuning. But you never know because it is still a black box. So, I mean, unless I'm unaware of some mathematical explanation of that, I don't think you can really be sure that you find the best one and, you know, just be humble and say, this is what we found, and yeah. I don't know.
Okay, thank you. One more question.
Thanks for the presentation. I just want to ask you which software you used for the developed this model.
For the
you partly answered after this. I guess Python.
So for the development of the model, we used TensorFlow, yes, and Python. Yeah. And instead for the fstat inputs, I can't go back. Anyway, for the inputs of the CNN, we used the LIGO Cloud Suite package. So we create the inputs with that, and then feed them into the Python software that we're making. Yeah.
Thank you.
You're welcome.
Okay. If we don't have questions, then thank you once again. It was very interesting. We are going on with Always Jelenka and his talk submission to the AML gw1.
Can you hear me? Now?
Yes.
Yeah. Laser pointer. I think I didn't turn it Oh, I forgot which one to point to was, sorry. Yeah. Okay, sorry, thanks. Hey. Thank you for the introduction. My name is Kizanka. I'm a PhD student working with Professor Bernd Brickmann in Jena in Germany. And first I will talk about the machine learning gravitational wave search challenge as an initiative, and afterwards I will detail a bit about the submissions that we are putting in. Is it all fine? So first about the challenge itself. It's an initiative to drive innovation in machine learning for detection of binary black hole signals in long segments of data, in the context of a search, mainly by the Albert Einstein Institute in Hanover, by Marlin Schäfer, Frank Ohme, and Alex Nitz, who is fairly known in these circles. And well, it's focused on purely detection, no parameter estimation at all. And there are several groups registered, and each group submits a Python script to produce a list of candidate events with their times and abstraction statistic. And these are then evaluated based on the false alarm rate, sensitive distance, and to a small degree also runtime. The submission deadline that's mentioned here, originally it was the 31st of March, so it was supposed to be over by now, but then it was moved 2 weeks, so the deadline is 2 days from now. There are still open slots, so if anyone is interested in participating, it's still possible to join, but at 2 days until the deadline, that might be a bit too late. If anyone is interested in the challenge anyways, then visit this link. The repository contains all the necessary information. One reason that pushed us to organize this challenge is that there was a lack of one might say unified testing in the community. So we're hoping that at one point it might be a good idea for new algorithms to also be tested on these data sets. So what the challenge actually provides for the evaluation are 1 month strains in both of the LIGO detectors, with injections generated with the Phenom XPHM model. And these datasets exist in 4 levels of complexity, from the simplest to the most complex. One of the things that drives this complexity is the noise. So in the first column, the 4 numbers, these are the numbers of the dataset. And the first level of complexity just works with Gaussian noise with a fixed PSE, while the 4th actually uses real O3A noise from O3 observing run. And the other thing that changes with the different datasets are the waveforms, moving from, again, the fairly simple, only the dominant mode with 0 spins to arbitrarily misaligned spins with all of the higher modes that the model can provide. So each group submits their algorithm. The algorithm is applied to 4 different datasets. And while the code to generate those test datasets is public, the final seed used for evaluation is of course unknown. And the result will be 4 sensitivity curves for each of the algorithms that will then be used for the final evaluation of the challenge.
I have a question on this one.
Yeah, go ahead.
What's the difference between the 3 and 4 level and group?
In the waveforms, there is none. So the waveforms are, I mean, the distribution for the waveforms is exactly the same in both 3 and 4. The data sets 3 and 4 only.
The real data, the real whole data.
Yeah, exactly. The difference is only in the noise. So I will move on to our team, which I very inventively named after our institute, where we simply following the footsteps of the paper we managed to get published this year in January, where we follow the footsteps of one of the pioneering papers by Hunter Gabbard and Chris Messenger and collaborators. I find it somewhat ironic that my talk was placed right after the previous one, because one of the things we did was do training strategies. So try to do fixed data set learning as well as curriculum learning. And we actually didn't find any benefit to curriculum learning in our specific application. The next thing that I took from that paper for the submission was what we call simply USR, or unbounded softmax replacement. The thing was that due to rounding errors in the final softmax layer in our network, our search, while it was training, suddenly collapsed and was absolutely useless with literally 0 sensitivity. And we devised a fairly simple fix for that. I won't go into the technical details now, but this was one of the key ingredients for our submission. And yeah, and what we also did in the paper was to actually test on longer segments of data, also the length of 1 month. So this has already prepared our way for the submission itself. And this testing on continuous data is done using the typical sliding window approach, where the whole long data set is sliced into smaller pieces, and the network is applied to each of them individually. And this is thresholded, and the triggers, one might say like level 1 triggers, are then clustered into what we then call kind of candidate events that are the actual output of the search. Here is where when one kind of interesting fact comes in, is that the first level threshold seems to be largely arbitrary. In fact, in the result that I'm going to show later, the threshold on the softmax output, so between 0 and 1, was somewhere on the order of 10 to the minus 4, which is very, very surprisingly low. But kind of a fun fact, fun, although very insignificant result, is that this has surprisingly low impact on the final result. So this is the plot we got in the paper we published, and this is also the kind of plot that will be used for the final evaluation of the challenge. And this also demonstrates where we had the problem with the rounding in the softmax layer. I will move on to a few technical details, which I will talk about very quickly. Again, we're working with 1-second segments at a sampling rate of 2048, as we did within the paper. The one big difference that we did was to actually use real noise for training. This didn't seem to have any effect on the results from on the data sets that used Gaussian noise, but on the test data set with real noise, this has made quite a lot of difference. For the waveforms, this generally tries to follow the distribution in the test data sets. We tried to teach the network to work with whitened inputs, and what we used was a balanced data set, so that we had the same number of pure noise samples and noise samples with injections in the actual training and validation data sets. And for the model, we took, again, a very similar architecture as in the paper. Here we also did not exactly grid search, but a couple of variations on the network's hyperparameters to find out that it was actually surprisingly useful to make the network twice as deep. But previously we had 6-layer convolutional apart. It turned out to be quite helpful to go for 12 layers instead. And of course, to use a 2-channel input, because we're dealing with 2 detectors, while originally in the paper we only did 1 detector. And to use a softmax at the end, although that is then removed for this testing. Binary cross entropy, same as in the paper. This is not a very innovative slide. And this is the final plot of the curves that we got. The jump from DS1 to DS2, 3, and 4, right? So this is one network tested on the 4 data sets of the mock data challenge. This one is simply caused by the PSDs in the 2nd to 4th data set being stronger than in the first one. The one still kind of bad thing is that with the data set 4, that's the one that uses noise in the test data set. There's this kind of crash again. When I was actually doing training with Gaussian noise, the same thing happened somewhere more like here. So this is where the real noise was definitely helpful in training, but apparently, at least in our experiment, there's something missing to really make this competitive. In some of these talks, I like to say that machine learning, that one of the reasons machine learning might be helpful is that it may be able to deal with non-Gaussian noise better than match filtering, right? Because match filtering has basically Gaussian noise as a prerequisite, while machine learning does not actually, in the general theory, expect that. So that's definitely not true in this case. So I will move a bit further. One other submission that I think would definitely be interesting is by my colleague Marlene Schäfer, who's basically the main organizer of the challenge, who who actually took the same network that we trained for the previous paper and used it to build a coincident search. So since the deadline was moved, we don't actually have the final results. I was hoping I would show an interesting plot here, but unfortunately that's not done yet. But for anyone interested in the topic in general, I definitely recommend you to take a look at the results of the mock data challenge. Another submission will be by a team named PyCBC, whose only member is Alex Nitz. So while it's up to him what exactly he will submit, I'm expecting it will be a matched filtering search, which will then provide a good baseline for these machine learning searches. So as a final note, I think this will definitely be interesting, and if anyone is interested in these searches, they should take a look at how the mock data challenge turns out. And that's it from my part. I will gladly answer any questions now or.
Okay, thank you for the talk. Thank you for this very useful information. Do we have? Yes. Okay.
I had completely missed that this challenge exists, and I was wondering, big picture, what's the differences to the earlier Kaggle challenge? Is the parameter range bigger or more difficult?
It's the main difference is in the whole context, because the Kaggle challenge was focused on isolated samples, while this challenge specifically focuses on longer segments of data and allowing for some more freedom in the whole algorithm of not just assigning probability values to isolated samples, but also with all this clustering and stuff.
Can I have a second question? The first reference that you have to the gw1 I saw you briefly had spelled that before, but I didn't quite understand how it comes in where you have posteriors.
Right. Okay, I will move a bit back. Ah, yeah, I must have skipped it. Oh. Yeah, here.
Yeah, you just showed very briefly, but you're only doing a search, you're not doing parameters, right?
Yes, that's true. The paper I'm referring to here, that's where they actually where they followed a similar formalism as in the previous talk, where they made hypotheses for pure noise or noise with injection, and where they have provided an argument that training a network with two outputs using the binary cross entropy laws and these kind of certain posteriors as labels is to some degree equivalent to working with callback divergence with the actual Bayesian posteriors.
Okay, thanks.
It's basically like an approximation method, but
yeah,
that's
so it's not posteriors of masses and spins, whatever. It's just the hypothesis tested.
Yeah, exactly.
Okay, Michael.
I have a related question to the number of the number one of the challenge. The one. So the second challenge are you already thinking about the second challenge? And will the second challenge be about parameter estimation?
I don't really know, to be honest. The name is something that Marlin made up, and I assumed that he had plans for something else. But I must admit, I have more than enough other things to focus on that I didn't even actually ask him. If there is a second challenge, I will probably participate, but both his and mine PhD time is growing shorter, so who knows.
Understandable, yes.
Okay, thank you. Agata.
Hi. So in the slide, I think 12, there was a plot with the different DS. Could you repeat which is for modes?
Sure. So both the noise and the waveforms grow in complexity from 1 to 4. The waveforms start with the simplest possible thing, only the dominant mode, 0 spins in the first dataset. In the second one, so in the orange line, there are also aligned and anti-aligned spins, if that's the word, and still only the dominant mode. And then the third and fourth have both have all the modes implemented in Phenom XPHM, and they have generic misaligned spins.
And the background?
And the noise in the first data set is all generated using a single fixed PSD as Gaussian. In the second and third, it's generated using PSD randomly picked from a set of PSDs derived from the O3A dataset. And in the fourth level, it's real noise from the O3A observing run.
Okay, so basically you observe this effect only when you use real noise.
Yes. Yeah. And this is what I tried to counter by training with real noise, because previously when I was doing the experiments where I would train with Gaussian noise, the lines for 1 through 3 are very similar to what they are right now, but the one for dataset 4 basically crashed to 0 somewhere around here, around 10 to the 4. Just odd.
And in this, you have the correction with the US.
Yes.
Okay, so it's not due to the softmax thing.
Right, it's not. The softmax problem actually, by its nature, would necessarily manifest itself at one point by just going straight down vertically, right to 0.
Okay. I have also challenged. First one who raises up the hand will get the phone. So I found the phone here. Okay, I will leave it to Isa. Oh yeah, okay. He won the challenge. Okay, so if we don't have any question, thank you once again. It was very useful and interesting. And last talk in this session is by Gregory Baltos. Did I spell correctly? Gregory?
Exactly.
Okay, okay. The talk will be about CNN for early alert going down in frequency.
Do you hear me? Yeah, it seems yes.
Sure.
So hi everyone. So today, so I'm Gregory Baltus. I'm working at University of Liège under the supervision of Jordan Kudel. And today I will present you a work that I have done with Gisela Jorca, Melissa Lopez, also Hafna Ola, and my promoter Jordan Kudel. So it's a good thing that I passed just after the previous talk because there are some kind of similarity between the two.
and complementarity, because here I will look for BNS and the previous one look for BBH. This talk will be divided in two parts mainly, because we have done two papers, one that we have present like a few months ago and published a few months ago, and we have built on the previous one to try to remove some limitation and improve the pipeline, make it more realistic. So first, let's begin with the goal and the motivation. So the goal of this work is to try to detect the early in-spiral phase of binary neutron star with convolutional neural networks. Obviously, the main motivation is multi-messenger astronomy. You want to build early alert system for the astronomer. So if you are able to detect a binary neutron star soon before the merger, you can send a message to the astronomer and say, oh, look in this direction in the sky, we perhaps observe an electromagnetic counterpart. Another question that we can ask is, why using deep learning? Actually, there are multiple answers to that. First, it's computationally cheap, especially after the training, compared you don't have to carry a whole template bank during the search. This is especially true for binary neutron star, because as the signal is longer, you need usually a bigger template bank. So you can analyze one frame of data, like 30 seconds, let's say, in less than 1 second. So that's for the motivation. So I just explained a little bit the previous paper. If you are interested, you have the title here and so the archive link. And so all the ideas, like kind of similar to the previous talk, we generated some noise. Here in the first paper, we generate some Gaussian noise coming from design sensitivity. We'll discuss a little bit later about all the PSD that we will use in the new work. You inject a binary neutron star signal, and obviously, if you want to detect produce an early alert system, you just select the very beginning. So for example, here between the two red lines. So you only have this spiral. We do some kind of preprocessing like whitening, high pass, low pass, and also normalization. And you feed all of that to a CNN. So the CNN is also trained like a classifier to distinguish between noise and noise plus injection. So that's a basic principle of the previous paper. But this paper also comes with some limitation, but before explaining them, I have to explain another important parameters, which is what I call the observation time window. So basically, it's the length of the signal that you want to feed your network with. So the network is made of convolution layers, but also of dense layer. And because of that, you need to always feed your network with the same length of input. And so this is something important to choose the right length. And there is some kind of balance here, because in one hand, you want to be able to detect an event super fast, so before the merger. So you want this time to be the smallest as possible, detect it quickly. But in another hand, you want that time window being big to be sure that the SNR accumulates enough so you can actually detect the signal. So you have some kind of balance between I want to be sure to detect and I want to be detect the signal fast. In the first paper, the problem was that the masses of the BNS influence the length of the signal. Actually, the length of the signal is linked to the chirp mass. And so if you take a minimum frequency for your waveform of 20 Hz, the length of the signal can vary from the simple to the triple. And so that causes some kind of problem when you have to choose this observation time window. So in the first paper, how we have solved this problem is that we divided all the BNS in 3 categories, depending on the mass, so light, intermediate, and heavy, and we train a network on each of those categories. So we have actually 3 networks with their own observational time window. And that could be seen as some kind of limitation, because finally, all the signal of binary neutron star is not that different. And you expected a single CNN to be able to recognize them. The only is the length of the signal and the frequency evolution. So let's speak about the other limitation of this work. So obviously, having 3 networks, it's one of the limitations. We also have considered only one detector, so Hanford, for example, and an optimal sky position. As I mentioned, frequency was 20 Hz. And for me, which is the biggest limitation, is the fact that we use design sensitivity PSD to generate the noise. We know that it's not super realistic. And so we can try to see if we can upgrade this stuff and make it more realistic. And it's exactly what we have done in our next paper. So I will discuss that now. So first upgrade that we make is that we're now using only one CNN to detect all the BNSs, regardless of the mass. How we have done that? It's quite simple. In fact, we just go down in frequency for the waveform, and we go down to 10 Hertz. And if you do that, all the signal will be obviously a way longer. And sufficiently long to choose an observation time window for a length of input, or for example, here 300 seconds. So with that, we can always see the inspiral without the merger for every type of masses. And so if you choose this time window, whatever the mass, the SNR can accumulate enough so we can detect the signal. And so on one network now, obviously we made some more realistic BNSs uniformly distributed into the sky, also into the spin, for example. The network has not changed that much. It is working quite well, just a little changing perhaps a little bit the kernel size and so. But it's still a few layers of convolution with also 2 layers to reduce the size of the data. This is kind of important, followed by dense layer at the end. The only difference, or one of the big differences, is that now it's taking account the 3 detectors. Just like when you do convolution network for image recognition, let's say, you can take a colored image and split in 3 channels, red, blue, and green. Here we do exactly the same thing, but for Hanford, Livingston, and VFB. You also know that in real life, sometimes 1 detector or 2 detectors are off. So we also train the network with some frame just is full of 0, so the network can also be continue to perform even if 1 or 2 detectors are off. So that's the idea of the amelioration, but a main goal of this paper is to try to say, okay, what's happening in more realistic scenario? For example, how our network will be able to build and find the early spiral phase in real noise of O3, for example. And what is the difference between real noise of O3 and if we just generate some Gaussian noise of O3? And obviously, as the goal is to try to run it on the next zone of observation, we also want to see what happened in O4. So here we have the multiple PSD that we use. The red one was the one of the first paper. The orange one is a PyCBC PSD that summarizes the real noise of O3. And from this PSD, we just simulate Gaussian noise. So it's a Gaussian noise O3. The blue one is just a representation of a PSD of some real noise of if I remember well. And O4, the green one is the PSD of O4 produced, given by the mock data challenge of O4. And here you have the different realization of the noise. Also, an important factor is that for real noise, we have tried to make it as realistic as possible. So we try to take the real noise coming from the low latency with the channel and the frame time that we have used right here. So that was the goal. And so another goal is to try to go down in frequency. What does that mean? Going down in frequency on the waveform, meaning trying to detect the events even earlier. And so, for example, let's say that you first analyze this frame, so the wet one, for 300 seconds. The network see only this. Let's also say that the maximum frequency of the waveform that the network see is 25 Hertz. He makes some prediction. You slide a little bit to your network, and eventually you arrive to the second frame here, so the green one. Let's say that the maximum frequency here is 50 Hertz, and he made another prediction. What we have found is that if we just make a data set with a uniform distribution of maximum frequency, the network is very good to detect those one, so the green one, but very bad to detect the red one. So as soon as you start to decrease the maximum frequency, the network is not as good. We think that is because the network is actually good to detect a change in frequency. And when you have a smaller maximum frequency, the change is also less strong. And so to solve that, we'll have used curriculum learning. So I will not explain again as a tutorial what is curriculum learning. I'll just show you a little table here. So for this curriculum learning, we not have done that in SNR, like in previous talk, but we have done that on maximum frequency. So we start with a data set with a quite high maximum frequency, and then we train the network on it, and then we add the second data set with a maximum frequency, which is a little bit smaller. We train on it, etc., etc. Yeah, TBM is 4 times before merger. Like in the previous talk, we train the network on O3A for the training on real noise, and we tested on O3B. So the noise is kind of a little different, and it's a good point to do that. So doing this curriculum learning, we actually performance for all the data. Oh, please. Okay. Except for a maximum frequency of 20 Hz, but I will come back to 1 second. So here I just show the 3 last data set. Actually, the other was exactly as a plane curve here. And so all the result is kind of similar. And when this is good, this is what we want, to be able to detect all the part of the waveform and also the most early. Except for a maximum frequency of 20 Hz, where we see that the performance of the network is not that good. By the way, this is the true alarm probability, so defined as the number of events correctly classified by the network divided by the total number of events. And I also have to mention what is pi SNR. This is the partial in spiral signal-to-noise ratio, which is exactly like the SNR of match filtering, except that you're looking just for the part of the waveform that the network sees, so the early in spiral, 300 seconds. And so this curve, so the one of a maximum frequency of 20, this time it's not because of the network, but if I go back some slide before, and you look into the PSD here, you see that at 12 Hz, we actually a huge peak in the PSD. That means that the noise is more difficult to deal with. And so this time it's not because our network has some difficulty to see this part of the waveform, but it's just because the noise is more difficult. And so that's a good point. The limitation coming now from the noise and not from what our network has learned. So as I mentioned, a main goal of this paper was to try to make a comparison between the different type of noise. And here it is. And what we first see when you're looking at those curves is that all the results seem kind of similar in terms of performance and by SNR, especially if you consider the two Gaussian noise case, where the curve is almost the same. And so what that means that if the network is trained on different type of data, it's actually sensitive to the SNR. And see whatever is the noise, if the pi SNR is kind of similar, you have similar results. This is not completely true for real noise, where you see that the performance is a little less good. For example, if you want an efficiency of 50%, you need a pi SNR about 17 or something for the Gaussian noise gain, and about 20 for the real noise case, where we can interpret that the noise is a little more difficult, it's non-Gaussian effects, you have also some glitches, etc. But still, the conclusion is that if you're looking for the early spiral, so some kind of sine signal with a variation of frequency, the performing in the real noise is quite similar to Gaussian noise. So that's, I think, a good point to know that if we go to real noise, the performance doesn't decrease too much in our case. So just to remind you how work this pipeline, so it's quite like the presentation we did before. We analyze, so let's say that you have a frame of 1,000 seconds. Let's say that in the beginning you see the first 100 seconds, you make a prediction, you slide the network. Actually, we choose a slide of 5 seconds, so we have a huge overlap. You make another prediction, and so on and so on. We also inject a signal starting at 10 Hz or perhaps even a little less. And as soon as our network seems to predict something, let's say that you have a 1 at that time, we compute the time before the merger, so the green stuff here, and we know how many seconds in advance we are able to detect the signal. The fact that we choose 5 seconds here is kind of arbitrary, but you can go under that. Actually, the minimum time that you need to choose is the time to load the data, pre-process it, and run the network over it. And all that stuff is quite quick, so you can reduce that probably to 1 or 2 seconds. So let's see another result where we have here the time before the merger. So what we have done here is exactly what I have described in the slide just before, but we take some always the same signal, or always the same masses for the signal, and we take masses similar to gw1 So the total duration of the signal is the same for all the signal that we inject here. We inject that in some noise, we pass our network over it, and we see the time before the merger that we are able to detect. Obviously, the best curve is for O4 Gaussian noise because it's Gaussian and it's O4, so it's the best PSD. Then you have Gaussian O3, and finally you have Gaussian O3. Real O3, sorry. If you look for realistic distance, so for example, tuple 40 megaparsec, which is the distance of the first binary neutron star, so gw1 you see that the two curves, so Gaussian O3 and real O3, is not that different. For example, at 40 megaparsec, you detect the event 25 seconds before the merger for real and 35 seconds before the merger for Gaussian. I think this is also a good result, or an interesting result. Once again, the difference between real and Gaussian is not that huge. And for O4, we expected to detect such an event 50 seconds before the merger, which I think is quite nice, almost 1 minute to alert the astronomer if this is quite cool. But we can ask, okay, we know that we are able to detect this kind of events in O3 or O4 Gaussian, but do we expect to see such an event in the next round of observation? And so to answer this question and to see if you are actually able to detect some event in O4, what we have done here is that we have simulated a population of BMS. Actually, we have simulated 5 years to have more statistics. We have injected that into some O4 noise, and we have passed our network over those frames and see how many it's able to catch and how many it's able to catch in advance. And so in 4 years of data, it's actually 14 events. So if O4 it's 1 year, it's roughly 3 events that we expect our network to find in advance. And you also see that if the chirp mass is low enough and the SNR, network SNR, is high enough, you can detect an event quite a while in advance. For example, this one almost 90 seconds in advance. But even if the mass is a little lower and the bigger, sorry, and the SNR a little smaller, you're still able to detect some of them 20 or 10 seconds in advance. So I think it's and so just let's speak a little bit about the next step. So one problem that we have still with our network is that the false alarm probability is relatively high. It's about 1%. That means if you analyze 100 frames, one of those frames will be classified as an event, even if you have nothing in there. And so that is a problem, especially when you want to design an alert system. You don't want to alert too often the astronomer. And so to reduce that, we try to think about some method, almost also that similar to the previous tool, that instead of taking one network with the 3 detector, taking account the 3 detector, we can build one network by detector and just see the coherent trigger, just like in match filtering. We also want to test our methods on the mock data challenge of O4 and perhaps other mock data challenge if they come in new other. We don't have done that, but we plan to do it soon. We investigate some new convolution network with, for example, only convolution, so no dense layer. So the length of input is less important and more complex input, but I will no enter to discuss that now. And finally, a very important question is the question of the sky localization, because if you do a pre-merger system, you also need to give a sky map to the astronomer. And this is a little more tricky to do when you only have the Orleans spiral and not the time of the merger. So we're working with Alex Colmus, which have just put a paper on, published a paper here, where we try to do some method to do the sky position with machine learning, but on the full signal. And we can see if we can adapt this method to produce a sky localization with only the Orleans spiral. So the conclusion, in the first paper, we have designed convolutional network to try to detect the early spiral phase of binary neutron star, but this paper was a proof of concept with a lot of limitation. In this new work, we try to remove a lot of those limitations. So for example, one network, we take into account the 3 detector. We try to go in dynamic frequency, meaning try to detect even earlier. We have tried to also see what is the performance of the network in different type of noise, real versus Gaussian, O3 versus O4. And one basic conclusion is that going into real noise doesn't change a lot in our case when we're looking for the spiral. We expect also to detect some events, some DNSs in O4, and if the SNR is high enough and the chirp mass low enough, we can detect them quite soon in advance, almost 1 minute, perhaps more, and we continue to investigate this work. So the paper is not on arXiv right now, but it's on the DCC, so if you are interested, we have the DCC link. So thanks a lot for your attention. If you have questions, please ask.
Thank you for this nice talk. Any questions?
It's closer.
Michael is waiting.
Good exercise.
Hi. So
Hi.
nice talk.
Thank
So
you.
I was thinking, no, when you presented the comparison between different noise type, right? It's not written in the slide, but I guess it's like the slide, the one before that, this one. So I think it's not written, but I guess the force around probability is fixed at the
Yeah, at 1%.
exactly. So I have the suspect that if you do that as function of the force alarm probability, you will see an effect like the one Andre was showing before. As far as the force alarm probability is relatively high, it's true that real is very close to caution, but I expect that when you require that the force alarm probability is lower, you will see an increasing of the difference. So it would be curious to check that.
That's possible. Actually, what we found is that for this force alarm probability of 1%, the threshold that we need to say, so the output is obviously something continuous, so between 0 and 1. And to obtain a force alarm probability of 1%, you already need a threshold which is very high, almost 1. It's 0.999, I think. So obviously, if we continue to try to decrease, the performance will become less good. But that's true, that it's possible also that the performance between real noise and Gaussian noise will be bigger in that case. It's something that we can check. But I think it's still mandatory to find another way to reduce this force alarm probability as just playing with the threshold. We're already almost at the maximum. Like it's very near from 1.
And have you thought about, so because this is CNN, right?
Yeah.
Maybe other architecture more, because this is applied to time series, not image, but time series. So maybe you could try some like network specialized for time series. There are a few.
We are also thinking. Sorry. We are also thinking about using some different kind of networks. So LSTM is usually a lot of stuff that we can use for time series analysis. I've discussed with some people that told me that just an LSTM alone, it's very difficult to train and to obtain good result out of it. So we're also thinking about combining, for example, convolution and LSTM. So the convolution can extract some information, and then you have this LSTM that can keep a track of the previous stuff that you have seen before. The fact is that for very long signal, it's kind of difficult because when your sample is, for example, here the sample rate was 250 or something like this. And so when the length of the data is very long, the LSTM cannot really keep track of what you have seen in the very beginning. So it's some kind of challenge that we're thinking how we can resolve that.
I said that because I tried with the, I will talk tomorrow, so I will show some other kind architecture. But the point is what you just said, all these architecture that focus on time series have really problems when you have too many points. So that would be a problem for you.
Yeah, I would be happy to listen to your talk then. Thank you.
Okay, Michael, here you go, please.
I have a question about the sky localization problem. So you mentioned this paper. Can you say a few words about how does it work? Is it triangulation? Because how does it work when you don't have enough frequency and not frequency of the waveform is not enough between the few detectors to make a triangulation that is usually done for sky localization?
So this paper was actually looking more for binary black hole, so not really neutron star. And so the idea was also some kind of convolution, but with three heads, if you want, at the ends. So one inferring the mean of the sky position, another one inferring the variance, and also inferring the masses. And so this kind of network is just trying to, and it do also important sampling at the ends to make the performance better. And what we have seen is that its performance is kind of near of the one of Bilby, but it's way, way faster because it's it's a machine learning algorithm. But that's true that if you want really just going for the early inspirer, you don't have access to the merger position of the merger, so it's not really triangulation, this work, because the machine learning do all the stuff, but it probably use the information when it sees the merger. And in the case of early inspirer, we will not have that, so that's another challenge.
I would imagine that if you have this early inspirer, maybe you can predict the end, and then use this information to triangulate something like that. Can that be a solution to this? Does it work like that, or is it something else?
So we don't have investigate right now how to do that properly, but yeah, this is something that we also can think about. Another thing is that also if you have the wave in the 3 detector, even if you don't see the end of the merger, you can see the different phase between the inspired part. And using this difference of phase could be also help to do the triangulation.
The difference of phase and maybe difference of amplitude is not such a huge because it doesn't really grow so fast. But yeah, but indeed for that probably you need to have enough signal to noise, and you go back to the square one, right?
Exactly. That's the thing is that even for this stuff we need a signal to noise ratio which is quite high, or the total waveform which is quite high if you want to see it just with a fraction of it.
Very nice work, but I guess you're getting in a very competitive field when you want to send out the real alerts. People will be really tough on you for any false alarms. So what's a false alarm range that this 1% translates to? How often would you send out a false alarm in calendar time?
Yeah, as I mentioned, the false alarm probability is 1%. That means when you analyze a frame, it's 1%. So I have to reduce the calculation actually. But if you slide by 5 seconds, you can evaluate this false alarm range. But I have to do the computation. I don't remember that.
Okay, so if it's per frame, then your global false alarm is actually quite high.
Exactly. It's why we really need to find a solution to that before making a real pipeline and for it to be competitive.
Can I have another question again?
So you mentioned the time to merger, but I didn't understand, is that just what you compare on your simulations, or can you also actually predict the time to merger?
No, we cannot predict it. So we can just say, okay, now we see something, and we also, if we continue to run our network, as soon as he arrives off the merger, just after, the performance drops. So we know that the event is finished, but we cannot predict the time before the merger, before actually.
Maybe third question. Okay, any additional questions? I think we can once again thank the speaker. Thank all speakers. So now we are about to conclude the sessions, and our Isa is going to do it.
Yeah, so local organizer issues. Well, thank you everyone, all the speakers. I think it's wonderful to have so many questions and so many discussions. For the people connected online, we will be back at 2:30, so in 1 hour and a half. For the people being here, as yesterday, you can take a lunch ticket from the table and go to the same place yesterday. So you know the path, and there are also some local people that can help you. Don't forget, please, to add your signature. So 2 things. For the people connected online, it would be nice if you put your real name, your real complete name, to identify you easily. I don't know if you are doing that, but please do it. For the people here attending in person, please don't forget to include your signature in the list. If you are not in the list, put your whole name and signature, so we are aware of everyone taking place in this conference. And then just a few comments about this afternoon. So this afternoon we will have one social event. I would like to give you, well, for the people connected online, sorry, this social event will not be streaming, so you need to be here in person. There is an extra, no, to be in person, so these are the social events. We will hopefully have more social events in future conferences, so for the people being here in person, just let me tell you, the social event today starts at 5. 5 in the afternoon evening. It's a room very close to the place we are going to have lunch. I can give you more details afterwards. The room is called Sala Darwin, biology. Well, anyway, it's very close from it's in the pharmacy. Very close from the place we're going to have lunch. You can be there like 15 minutes before. Just a few points. So there will be a very short presentation, like we're going to watch a short movie, then we will actually show the short movie, and then will be a round table. The language used will be Spanish mainly, because it is addressed to students in the campus. So if you don't want to attend, it's okay, no problem. You can, I mean, for people not speaking Spanish, you can take today as a free afternoon, evening. Anyway, you are invited to go, just to let you know that the short movie is in English, but subtitles and the language used for discussion will be mostly Spanish, because it's addressed to students in the campus. Don't worry, because tomorrow we will have the same event, basically, but everything in English, in another room, which is, let's say, addressed to researchers and professors. So we will have the very same structure. Anyway, basically, just to give you all the details, I think you can go tomorrow to the short movie premiere. But if you want to come today, no problem at all. So you will be able to follow the short movie, but maybe not all the discussion, just to let you know. So for people visiting us, sorry for the weather. I really tried hard to have some sunny weather. But on Sunday we had a little, not too much. Anyway, I think it's not so warm, so you can really enjoy having a look to the city. If you have any question about local tourism or whatever, I can also help. 5 minutes, okay, everything 5 minutes. So I think I had mentioned everything I wanted. Any question, any point, I am here to help you as much as possible. To the people connected online, see you in half an hour, in 1 hour and a half, sorry. And to the people here, please don't forget your ticket for free lunch. Okay, see you later.